I'm Andrea López, and I'm going to be speaking about how we can use very simple X-ray sensors to detect an object in the vicinity of a spacecraft. The regions of interest here that we're going to focus on are geo and more generally cislunar regions, and we've learned that there are artificial debris present here, natural debris, there are other spacecraft around, and it wouldn't be realistic to think that we can have a 24/7 surveillance on our spacecraft and its surroundings. So be it for the spacecraft own safety, be it for active debris removal, for any proximity operations, it would be convenient to have the capability to detect the objects that are around our spacecraft. And I'm talking about ranges of hundreds of meters. There are energetic electrons present in the plasma in the regions that we mentioned, and these energetic electrons interact with matter and in a bunch of different ways. One of them excites the emission of characteristics X-rays. One of them excites the emission of Bremsstrahlung X-rays. So what we're trying to do here is exploit these natural interactions that already happen with the space environment and use that to detect these target objects around our spacecraft. But typical X-ray sensors used in space are for astrophysics applications, and they have very narrow fields of view. And here we are going to be considering sensors with the field of view that go from a few degrees up to tens of degrees, but this is still not enough for what we're intending. So we thought, why don't we just throw a few of these sensors together, kind of in a coarse and sensor assembly fashion, and see what we can do with that. It's also worth mentioning that the signal for these coarse and sensors is typically following a cosine law. But in our case, since our intensity of the signal is going to depend on many other things, going to depend on the size of the target, the distance to the target, the local current plasma conditions, we are just going to model this signal as an on and off signal, as you can see here in the right, where the signal here is 1 when the target is within the field of view of that sensor, and it's 0 when it's not. This is for an example of 4 sensors with time. So what we are going to do is record the signal acquisition and loss of signal events, because we know that at these points the angle between our sensor and the heading of the target is going to be f. Here f is the half cone of the field of view. So by collecting all of these measurements, putting them all together in a matrix vector form, we can very easily solve for the heading. And in here, by the way, we're assuming that the target is a point source and it's static with respect to the spacecraft. So we can just do a batch least squares to solve. What does this cluster of sensors look like? Well, the orientation of each sensor is defined by 2 angles, which are the azimuth and elevation with respect to the platform in which they are stuck. And since we want to record these trigger events of loss of signal or acquisition of signal, we're going to have this platform in which they are mounted to be rotating at a constant speed about the normal to the platform, in here NP. We are also going to define a preferred direction, a nominal direction in which we want to make sure that we're detecting if an object is in that heading, and that assuming that this platform is mounted on the spacecraft plus Z side, this preferred direction is going to correspond with the Z-axis, the positive Z-axis of the spacecraft, which in this case, it also corresponds with the normal to the platform and with a an elevation of 90 degrees. So it's in here, it's this direction. We're going to study two different types of configuration, which are pyramid and elevation distributed. And I'll just go ahead and show you what this looks like. Pyramid configuration is, again, inspired in the classical pyramid assembly of CSS. And as you can see, well, the field of view here in this example is 10 degrees, and these are 4 sensors, and they are rotating about the normal to the platform, and the platform is assumed to be the XY plane in here. So since we are only recording the on and off triggers, and this is what we are using to solve, we only have 2 unique measurements, because the on and off of one sensor is then going to be repeated for the other 3 sensors. And in the end, even though we have 8 different measurements, we only have 2 unique measurements, and the rest are repetitions of those 2. In this plot here on the top left, I'm showing for different elevation and azimuth of the target, how many sensors would be able to see it. And you can see how we only have this narrow band in which the target would be detected. But since we only have 2 unique measurements, this is an underdetermined problem. And so the solution that we find is a minimum norm solution. And therefore, it's just going to be in here, in this case, the 45 elevation degree solution. And when the target is not at 45, but it's at 55, it's still going to think that it's still going to give us the solution that it's at 45. So then we would have a 10-degree error. And this is what's shown here. As you can see here, too, in the top graph, there is no dependency with azimuth. So in the future, I'm just going to show these plots with elevation in the x-axis. So having all of these sensors with the same elevation does really not help. We're just getting the same thing repeated. So we decided to put them at different elevations and just see what solutions we get with this, what results we get with this. So if we position these sensors so that there's no overlap between the sensors, then the problem is mainly underdetermined in this whole section of elevation. We only get 2 unique measurements all along, and in exchange, the coverage is maximized because they are covering as much elevation as they can. On the other hand, if we have an overlap between the sensors, then the only undetermined areas are where only one of the sensors is able to see, and those are these areas. And the error where there's an overlap goes to 0, as you can see here. So this minimizes the error in the area covered. So there's clearly a trade-off between maximizing the coverage and minimizing the error. And there are parameters that we can play with to see how they affect these 2 metrics. And that's basically what we are doing in the following slide in here. Here we create a design space for varying field of view of the individual sensors and varying angular separation between the sensors. And in the left, you can see this is coverage defined like here for the upper hemisphere, and the right plot is for average error in the area covered. Seems counterintuitive to see here in the coverage plot how for increasing values of field of view, the coverage is actually decreasing, but this is explained by 2 things. One is that the coverage defined here is just for the upper hemisphere. So once sensors go beyond the 0 elevation and go into negative elevations. This is not taken into account here. It's not accounted for in the coverage. Another reason being that when the rotation angle, the rotation axis is within the field of view of one of the sensor, this creates an area, a cone angle, in which the sensor is always active for that region, and we do not get any triggers. And I'm going to show you this in here. Here the upper sensor is going a bit beyond the 90 degrees of elevation, and so you can see now in the animation in the right how in the circle marked in red, you see how the rotation of the sensors does not make this area go in and out of the field of view of this sensor, and therefore there are no trigger events of loss of signal or acquisition of signal, because it's just always active. So which is the optimal point in terms of field of view or separation? Well, that will have to depend on the application in hand. If small errors are acceptable, then we can play with the underdetermined areas. So there's no one unique, one optimal point for this problem. We also, it's worth noticing that if we define the plus z direction as our nominal direction, we just saw here how we either this direction is not within the field of view of any of the sensors, or it is within the field of view, but then it creates a blind spot. So this preferred direction is not observable with any of the configuration seen, and this is pretty bad because it's the one direction in which we wanted to make sure that we are detecting objects. So many possible solutions for this: more complicated motions of the platform, tilting the platform and then rotating, etc. But we decided to just throw in some more clusters and see what happens. So now we are going to talk about 4 different case studies, all with the same number of sensors, but distributed differently in clusters. There's going to be a study case with 2 clusters of 6 sensors each, one with 3 clusters of 4 sensors each, one with 4 clusters of 3 sensors each, and one with 6 clusters of 2 sensors each. And the geometric constraints are set so that the blind spots for one of the clusters is covered by all of the remaining clusters. So this is what I'm showing you in here. This is for the case of 2 clusters of 6 sensors. So the preferred direction is marked with the X, and here on the left we have a unit sphere around the spacecraft that marks how many sensors would view a target that is in that particular heading. So for the nominal direction, we have 4 sensor visibility, so fully determined. Here you can see how there are a couple. In the right, you can see how there are 2 underdetermined areas within the northern hemisphere, but that could be solved by moving the clusters closer together. That would also result in a reduced coverage, but that's what we're playing with. And in here, we defined coverage, this number, not only in the upper hemisphere, but in the full sphere, because as you can see, the sensors are sensing beyond the 0 elevation point. And this is the, also shown here is the mean error obtained for this configuration. Same thing for the 3, 4 sensor clusters. We also have 3 underdetermined spots in the upper hemisphere, but they are smaller in size. You can see here how the nominal direction is perfectly covered, and we see a slight improvement in both coverage and mean error metrics. For 3 sensor clusters, no underdetermined spots in the upper hemisphere, a little bit better in coverage, a little bit better in average error. 6 2-sensor clusters, also no underdetermined areas, little bit better in coverage, little bit better on mean error. Does that mean that this is the best configuration? Well, that depends. The improvement in coverage and mean error is very slight from one case to the next, and adding additional clusters means adding additional moving parts, which means adding complexity, adding risk, adding cost. So I'll leave it up to you to decide which one is better. So what we've learned is that pyramid configuration, not a good choice for this problem. So distributed in elevation is the way to go. There is a trade-off between coverage and average error. And also with a single cluster, the nominal direction, it's unobservable. So with multiple clusters, we've seen that this solves that problem, and also increasing number of cluster. There's a trend that with increasing number of clusters, there's an improvement in both coverage and average error. But is it worth it? Well, I don't know. Just that also increases the complexity and the risk. Future work is going to be adding a dynamic target instead of a static target, and to do so, we're going to implement Kalman filtering and time-dependent things. We're going to be doing some experiments to characterize the acquisition and loss of signal events, and how the addition of baffles to our sensors affect the signal. And in the future, we'll also like to do a deeper analysis of how these different plasma environments affect our signal intensity and what kind of signal intensity we can expect in the different regions. So if you have any questions, please just email me anytime.